Okay, so this is the block diagram where basically here we have two streams coming up. So we have the stream number one, which is pure concentrated liquid, and maybe this is a liquid which is water. Okay, so that we get the desired amount of solution. Okay, or other way around, like suppose this is the water, so we want water to be continuous. So this is the water which we want to you don't want to disturb. So this is the constant solution. So depending upon what you want, you can mix, you can pump required amount of constant solution so that we get a desired solution. Okay. So because you want to control this, because we don't want to because we are not monitoring the output, we want to monitor the input. Okay. So if you want to know how much concentration is getting, that means we should have an instrument which can measure the concentration. Okay, so here is X is the concentration. So we are assuming that this whole tank is perfectly mixed and there is no heat losses, everything. So when it's perfectly mixed, the concentration is uniform. So we need an instrumentation basically, which is called as transmitter. And then we have XM, that is measured composition. And we check whether this composition is as close as the set point. Okay. If it is not, then we need to change according to the control. So we have a controller, then we have ITP converter, and then we have the control wall. Okay, so this is what actually we covered in the all the previous systems. Okay, so again today also we are going to much focus on this system and how we are going to build up a complete closed loop feedback control system. Is it okay?
Yes, sir.
Yes.
Okay. So for the same system, if you can write the material balance, what is the material balance for this? What is the material balance? Accumulation is equal to?
Energy in.
No, mass flow. We're writing about
mass
the
flow.
material balance.
Mass flow in minus mass flow out
is rate of accumulation.
Yes.
Yeah. Okay. So what can be the equation? Okay, I think because we are talking about components, better we write a component mass balance because we have X1 and X2 compositions. So what is the composition mass balance? So composition mass balance is X1 W1 is a stream 1 plus stream 2 is X2 W2.
W2.
Okay, so these are the input streams minus what is the output?
XW.
XW is equal to, okay, is rate of accumulation. Rate of accumulation is dm by dt. What is mass? Mass is nothing but volume times density. So we can take out the density out. So this is dv by dt because volume is changing. Okay. So now we have two equations. The first equation is your material balance equation, that is rho dv by dt is W1 plus W2 minus W. And here, because your second equation is component mass balance, that is VCA or Vx. Okay. So if the volume is constant, then which means that the material balance equation, first equation, you get that this is equal to 0. So then we get W1 plus W2 is equal to W3. Okay. So now if you substitute in this equation, second equation, so you'll be having everything in terms of W1 and W2 because this is 0. Okay. So because this is equal to 0, that means your W is equal to W1 plus W2. So if you substitute W in the second equation and you can just rearrange it, you get a term called as W1 times X1 minus X plus W2 times X2 minus X. So this is the component mass balance for this. Here we don't need to do energy balance because here do we have energy balance? There is no information about temperature. Okay, we don't know what the temperature of inlet, we don't know what the temperature of outlet, and so on. So that means there is no information about temperature. So we don't have to worry about thermal balance or energy balance. Okay, so if we apply Laplace for this and just rearrange it, so this will be the equation which we already saw in the previous units. So outlet stream is equal to stream 1 times the first order equation plus stream 2 times the second order equation. So this is the first order equation in respect to x1 and this is equation with respect to W2. Okay, so you can write in terms of W2 or you can write in terms of X2 also, because here we have two streams. So your stream 1, stream 2, depending upon the stream 3, which is your X. So this is X1 and this is your W2 or X2, or you can write in terms of any of this. So if you write this, so that means this stream is function of the first order transfer function with respect to x1 and transfer function first order transfer function with respect to W2. Okay, so here if you just simplify that, you this tau is nothing but V rho by W and K1 is W1 by W because these are steady state values. Okay, and K1 and K2 is 1 minus X by W. So these equations you can easily get it based upon the procedure which you followed in your unit number 3, how to derive the transfer functions for and how you can apply Laplace transform and then simplify it and then you get these equations. Okay, so that we already done it, so I'm not focusing much on that. So here what we see is the output x dash, the deviation variable, is first order with respect to x1 dash and first order is respect to W2 dash. That means stream 1 and stream 2. Okay, so you can derive it later on. We don't have to worry about that. So, but we just have to say that stream 1 and stream 2 are having first order in terms of output X. Okay, so let's continue. So, which means that your output X dash is nothing but sum of two streams, which is this. So transfer function K1 by 2s times X1s and K2 times W2. So if you just add these two is your X. So this is the mass fraction of the simple system of the process. So this is only just a process. So this is the process diagram. Okay, where we have two streams and we have one outlet. Okay. So here we consider this as D because we are not focusing, because this is like a disturbance. Okay, we are only monitoring only one variable, that is your X2 or W2. Okay, so this is your XU and this is your XD. So we are controlling only this variable. We are not controlling the XD. Okay, so this is the process. So that means now we have a block diagram for the process. Okay, so for how many participants? 24. Okay, so now what we done is we just draw a block diagram only for this process. Okay, So now we need to derive for each component. That means we have a sensor, we have a controller. So we should have a one block diagram for controller. We should have one block diagram for sensor, and then we should have one block diagram for the final control element. Okay. So now let's focus on the composition sensor transmitter. So that means we have an instrument here which measures the composition and transmits. Okay. So here the inlet is X because this is the X here, and the outlet is XM. So your XM is transfer function of XM by X is nothing but you should find the transfer function of AT. Okay. So we assume that the relation between this AT is also a first order transfer function. Okay. So what is first order transfer function? Which has the form of something like S plus something. Okay. So if we have a transfer function of S to the power of 1, then this is a simple first order transfer function. So for that, it may also have time constant, that is tau, and it may also have some steady gain, which is k. So the k can be different, your tau can be different, and your here it should be 1, so that it's in the form of the standard form of k by tau s plus 1. So if we assume that this transmitter, the composition sensor transmitter, is also a first order transfer function, then we can write it as xm by x, that means xm, that is output by input, is km by tau ms plus 1. Okay. So since because here we are focusing on measurement, so we put subscript m. Okay. So this m stands for measurement. So that means this is the steady state gain for the measuring element, and this is the time constant for the measuring element. So this is the transfer function for the sensor transmitter. Okay. Is it clear?
Yes.
Okay. So my
Yes,
video
sir.
is going. My video going to end in 10 minutes because I started late. Okay. Yeah. In 5 minutes we'll just give a break and again we start again. Okay. Let's first continue this. So far what we've done is we draw a transfer function for process, and we also got transfer function for the transmitter. Okay. Now let's move to the next component, which is your controller. Okay. Okay. So this is the block diagram for the transmitter. So we have outlet, we have this is output, this is input, and this is the transfer function for the corresponding transmitter, where Km is the steady state gain of the transmitter, and tau m is the time constant for the transmitter. Okay. So the third component which we are going to write the transfer function is the controller. Okay. So here the controller can be a simple proportional controller. It can be PID, PD, or PID. Okay. So for time being, we just assume that it's a simple proportional plus integral controller. Okay. So proportional for integral controller, what is the transfer function? We already got that. It is nothing but Kc times 1 plus tau I s s. So the first one is proportional. This whole thing is your integral term. So this is the transfer function for the PI controller. Okay. Again, we also covered this in the previous unit. So we're just putting everything together. So far what we've done is we just finished writing a block diagram for process. Then we draw we found the transfer function for the transmitter, and we also draw the process flow for this, and then we also looking at the controller. Okay. Of course, you know what is P, what is E. So P is basically the output, and E is your error. Okay. So that means you are relating between pressure, which is our pressure here, output term, and E is your error term, with error signal. So output by input is nothing but Kc times 1 plus 1 by tau I s. Okay. Because why you need P? Because here we need to convert your pressure to I to P converter. So this I to P converter needs pressure, and then it will supply the pressure to this, and then your control valve is going to open. Okay. So far we just we just had 1, 2, and 3. Okay. Okay, so now I'll just stop. I'll disconnect it because the time is running out. So I'll again send you a message for the meeting because it's almost 40 minutes already. So just wait for 5 minutes and we'll continue again the new session.